So now we're going to talk about Bayesian statistics. You've probably heard about these, even if you've never seen or experienced or used them yourself. And Bayesian statistics, you notice when we're talking about traditional statistics, there's a lot of unknowns going on. We'll talk more about this in a bit, but Bayesian statistics tries to put a number on it. I kept saying things like, when you say p is less than 0.5%, you don't mean that the probability of. Bayesian stats wants to put that number on. It wants to say there is a probability, and that's the probability that your new system is better than the old one. And it tries to put a number on it. In doing so, it has to make some assumptions, and we'll see how these work out. So just to give you an idea, I'm not quite sure if human-computer interaction includes Martians, but anyway, human-Martian interaction example. I'm going to say, and the probability of a Martian having an antennae is 1. As far as I'm aware, every Martian that's ever been observed has antennae. So I think I can win that. So I think Martians have antennae. Humans, I'm going to give them 1 in 1,000 of if you having a human with an antenna. Actually, it's probably less than that. Let's go for 1 in 1,000. Maybe there's some strange genetic condition and certain occasion you get people with antennae. Maybe they're just dressed up for a party. But anyway, we're going to go for 1 in 1,000 that a human has antennae. And Martians, 1, they're bound to have them. If you meet a Martian, it's got antennae. So my null hypothesis, is that there are no Martians in the high street. And the alternatives is that the Martians have landed. Okay, so now I'm wandering down the high street and I meet somebody with antennae. With traditional statistics, right, what's the likelihood of meeting somebody with antennae, given they're human, is less than 5%. It's 0.0. In fact, it's 1 in 1,000, so it's at 0.1%. But it's certainly less than 5%. It's less than 0.1%. I'm going to reject the null hypothesis that there are no Martians in the high street, and I'm going to call the men in black. You sort of probably feel this is overreacting at that point. You probably could give a little tug on the antennae first. In fact, science fiction stories are full of people just never actually believing that things are going, strange things are happening to them. So you probably wouldn't go. So it gives you a sort of feeling that perhaps I don't always want to do what traditional statistics tells me. Bayesian statistics does this differently. So a Bayesian approaching this would say, well, how likely? So I've said, you sort of know that it's probably not going to be a Martian. How likely am I, if I meet somebody in the high street, for that to be a Martian? Put a number on it. This is called the prior probability. You sort of know that it's unlikely to be a Martian, and the Bayesian says, put a number on it. So I'm going to put some numbers on it. So I'm going to say the probability of meeting a Martian in the high street is 1 in a million. Possibly it's 1 in a billion, 1 in none. Perhaps it's impossible because there aren't any Martians. But I'm going to go for 1 in a million just as a round figure, because I need to put a number down. Because that's a Bayesian, I want a number there. And the human, the probability of it being human is the rest. It's 999,999 times out of a million, it's a human. Okay? I'm going to take my same probabilities for effectively it's the conditional probability or the likelihood that if it's a Martian, it's likely to have an antennae. It's bound to have an antennae. If it's a human, 1 in 1,000 of having an antennae. So as well as that information I had before, I've also got this prior distribution that says how likely is it that somebody I meet will be a Martian. I meet somebody with antennae. So there's only a 1 in 1,000 chance that if a human's got antennae, that human that I meet will have an antennae, but I'm a million times more likely to meet a human than a Martian. So I end up with a posterior probability, one that after, so before the event I thought, well, it's a 1 in a million chance I'll see a Martian, and then I see this thing with antennae. So I've now got a posterior probability, one that I've worked out. I said, well, there's still this chance it's human. In fact, because there's a million times more likely to be a human, even though humans have only got 1 in 1,000 chance of an antennae, it's still 1,000 times more likely to be a human than a Martian. So I end up with this posterior probability. It says the probability of being a Martian is 0.001. It's approximately, it's not exactly this, but it's near enough. 0.001, 1 in 1,000. The probability of human, 999 out of 1,000. Bayesian stats at work. Right? No Men in Black this time, we'll say. So you can put different numbers in, you can put different priors in, you get different answers, obviously. What Bayesian inference is doing the same job of turning back from your measurements to the real world. So you've got your real world, you have random effects to get sample data. But in turning things back, in trying to then tell you something about the real world, it asks you, or perhaps an expert that you've recruited, to put a number on it, to say, what's the prior distribution? How likely is it that certain things are happening in the real world? Right? Then, given that prior distribution, but also given the known likelihoods of seeing data, given what might be true in the world, you put those together and then you create this posterior distribution. So again, think about my coin. I mean, my likelihood that this is, you can't see it, but if I just grabbed a coin from a bag in the bank, the likelihood that it's got two heads would be very, very low. It might happen, something goes weird at the bank, or somebody's put a trick coin in and it's got mixed up with the bank's coins. Very, very low. So a bit like the Martian, I toss it 1,000 times, and they're all heads, I'm going to think it's probably a two-headed coin. If I toss it just 6 times and they're all heads, it's not going to go with it. So my prior distribution, my idea of how likely it is influencing the way I build that posterior distribution, my belief about likelihood and probabilities after the event. But the difference between Bayesian stats and traditional hypothesis testing is it really puts a number. You notice that the probability of that's a Martian is 1 in 1,000. The probability it's a human is 999 out of 1,000. An actual number. So let's see this at work. First I'll do it as more as a tool for building user interface. This is an intelligent user interface. So imagine I want to build an adaptive website. I've got here is the Isle of Tarry website. Discover Tarry is sort of like the tourist board for Tarry. And this is not adaptive, but imagine I wanted to make it an adaptive website that did different things depending on the kind of users that were coming along. So let's look down quite low down. There's a menu item called Sports and Leisure. Now we know people tend to hit near the top. However, Tyree has big beaches and quite a lot of surfers come here. So surfers quite likely are to jump for that. And in fact, so there's the page popping up, and we do some surveys, how we get this data. But we've done a significant amount of work, and we've worked out that when a surfer visits the Isle of Tarry website, the surfer has a 75% chance that the first link they click is that sport and leisure one. Even though it's low down the menu, of course their eyes pop out and say, aha, that's probably for me, right? So I'm going to say when a surfer visits the site, 75% of the time, sports and leisure, bomb. Other kinds of users, non-surfers visiting the site, about 12.5% of the time they click that. That's sort of 1 out of 8. The rest of the time, I click accommodation or something else. I might be even lower than that, actually, in reality, because it's so low. We'll go for this 1 in 8 figure here, right? So imagine those are solid data too. I've really gone out. I've perhaps got some surfers in, instead of saying, here's a website, play with it, and just watch them and see what they've done. I've got some solid data on that. So imagine now I've got some other solid data, and this might be based on some sort of survey. Again, I did a visitors to the website, but I just happen to know that 20% of all the visitors to the website are surfers, and the others, 80%, are non-surfers. They do different things. Perhaps, perhaps they're coming to see the corncrakes and the birds on the island or something like that. So visitors to the website, 80% of them aren't surfers, 20% are surfers. Yay. So now imagine 100 visitors coming to that site. Of those, on average, about 20 are going to be surfers. On average, about 80 of them are going to be non-surfers. Now, remember the numbers I had from the previous slide, right? If a surfer comes to the site, 75% of the time, first link they click is the sports and leisure link. For other people, just 1 in 8 times. So of those 20 surfers, probably around 15 of them are going to click sports and leisure as their first click. Whereas of the 80 others, only 1 in 8 of them, that's 10 of the original 100, are going to click that sports and leisure. So of the 25 people, of the original 100 people, of the 25 who have clicked sports and leisure, 15 of them are likely to be surfers on average, 10 of them on average are likely to be non-surfers. So we've got a posterior probability distribution. After that, we knew what the original distribution was, the likelihood of a visitor coming to the site. Combine that with knowledge we had about behaviour, and we can get a posterior probability that says if somebody's come to the site and they've clicked sports and leisure, there's a 60% chance that they're a surfer and only a 40% chance they're not. Now you can start to see how we might change the site. We now know something about them. I mean, even when they visit another page, the visit an accommodation page, we might want to point them towards accommodation that's close to a surfing beach. We know things about them. It actually probably tells us a bit about their age, their style of doing things. There's all sorts of stuff we might know about them because of that. But you notice without any knowledge, 80% of our visitors are non-surfers, only 20% are surfers, whereas suddenly, because of what this person clicked, you've got a better idea of who they are. And of course, this is exactly what you see in so many websites, social media applications, e-commerce sites and stuff that make recommendations. They're using this kind of reasoning. So that's the sort of using it to do something. But that's a use of probability in intelligent interface design. But what I'm going to now do is then go and say, well, okay, let's use this for statistics, this is not quite the same as what we've been doing with the other kinds of statistics. So let's do a sort of standard one. So we're going to have our system A, system B comparison. We're going to have that. So what I'm now going to ask you to do is you've designed system B, your new flashy system A. How confident what's your belief about the likelihood, the probability that system B is better? So maybe you think, well, I was a bit uncertain when I was doing some of this. Maybe I haven't done it much better after all. So maybe you think, well, I think it's probably about 80% chance that I've not made a ha'porth and it's just the same as the old one. And perhaps a 20% chance that I've actually made a difference. Your prior distribution. Now you run your study. So and we're going to do a very small study. We've got 4 users, right? Maybe do some other things with them as well, do some rich ethnographic analysis of them, big observations, lots of video. But we also just asked them at the end, which system do you prefer, A or B? And all 4 of the users said they liked system B better. It's nice to feel if you've been involved in the design of it. So the probability of that happening is, if system A and system B, if there's no difference, then some people are going to say, I'm going to put my coin out, it's just like tossing a coin. Some people will just on margin like system B better on that day, some day, but nothing in it. It's like tossing a coin. The likelihood of the coin being a B all the time, if they were the same, only 1 in 16. However, and here are the calculations of this, because there are many ways, there's only one way of being the same in a sense, but there are many ways of being different. So this is a made-up figure. The first one's an accurate one. This is a made-up one. There are ways of dealing with this, but I'm going to just say that if B is better, perhaps sometimes you get people, they still, even though B is better on average for most people, some people might like A better. So I'm going to say it's not that it's absolutely definite that overall said, yay, I like system B. But I'm going to say the likelihood that all 4 like system B is pretty high because system B is better. I'm going to put a figure of 3/4 on that. So I'm going to say so if system A and B are the same, then the likelihood of them all of the users liking system B is 1 in 16. If B is better, then the likelihood I'm saying that they're all the same is 3/4. And they did all say the system B was better. What I can then do is, just like I did with the website, is combine that with those prior distributions. So effectively I'm going to multiply that 80% by the 1/16. I'm going to multiply the 20% by the 3/4, and then take those two numbers that I get out of that. And if you do your 1/16 of 80%, that gives you this 20. Forget what the 20 means for a second. 3/4 of the 20%. Sorry, 1/16 of 80% is 5. 3/4 of 20% is 15. So my posterior probability, my likelihood now. So I started off thinking, well, the likelihood is 80% certain that A and B are the same. I've now got some evidence that B is better. I combine that evidence that B is better with my prior distribution, and I get a posterior probability that says, actually, having done that, now I think there's a 75% chance that B is better. The ratio between those, that 75 or 25, is sometimes called an odds ratio. So it's 3-to-1. So, and 3-to-1 is better than evens, but it's not that brilliant. So you probably aren't going to put a lot of resources. You're going to perhaps want to find out more, double check. You usually want a much bigger odds ratio before you start saying, yeah, I'm now really, really certain. But your belief has increased that B is good. This has increased your belief that B is actually going to work. And perhaps you'll get some other data that will further increase it, hopefully. Let's do the same thing now with a different prior, because it was dependent on you at the beginning saying how, before I start, what's my belief? What do I believe is the probability that B is better? So imagine you were a bit more gung-ho and you'd done stuff by the book and you thought, wow, I've done all the heuristics right, I've got everything. I think, and I interviewed a gazillion users before I ever started designing it and really immersed myself in their sort of cultural context. I believe I've done a good job in designing my system. So perhaps you think there's an 80% chance that your system is better and there's a 20% chance that it's no different or perhaps even worse. Go for no different. But imagine, so that's your prior, but the study was the same, and in fact, it is the same study. It's just what assumptions you made before you start. So we've got A and B the same, 16th. If B is better, the probability of them all saying that preferring B is 3/4. So it's the same as we had in this last slide. Only those highlighted things are different. But now you do your multiplying up, turn the handle, and you get your posterior things. So we thought initially that the probability that B was better was 80%, the probability that there was no difference was 20%. We've now got additional evidence that B is better. You multiply up your 16th by the 20%, your 3/4 by the 80%, turn the handle. And actually we have this posterior probability now that says A and B are the same, is 2%, and the probability is B are better is around 98%. And the odds ratio turns out, given the numbers I put here, exactly 48-to-1, which is pretty overwhelming. It's pretty overwhelming, but it was the same evidence. The difference is, so you've got the same evidence, you ran the same experiment, first time, second time, the evidence you had was that 4 users said they preferred system B. But because this time you had more belief that system B was better to start with, you end up with saying, now I feel I have overwhelming evidence that system B is better because of the additional things. So your belief before has been factored into that confidence you have at the end. So the strong thing here is these are probabilities, given the prior probabilities. So where do you get this prior from? So I sort of think, well, I think this system is better. Sometimes there is a very clear prior. So like the people coming to the website, we know via previous survey, whatever it is, what the likelihood is and what the probability is that when somebody comes to the website that they're going to be a surfer or not. So sometimes you have very solid knowledge. Other times what you do is you take that vague feeling. So like with the Martian, the fact that you sort of know it's unlikely to be Martians. With the coin, you sort of know it's unlikely not to be a fair or nearly fair coin. and you put a number on it. Sometimes, if there's a lot of evidence, it doesn't make much difference what prior you put in, because the evidence takes over. Having said that, if the evidence is that strong, often, I'm not saying you shouldn't do statistics even when the evidence looks strong. It's worth doing it because sometimes, as we've seen, things can be confusing. But to be honest, if the evidence is that strong, the stats is just a little check you're doing at the end. So if the evidence is very strong, then it doesn't make a ha'porth what prior you choose. But as we saw there, for a piece of evidence, the two priors we had made a big difference to the results. So the priors are important usually, sometimes not. Traditional statistics they're not quite the same, but if you have what's called a uniform prior, so if you assume that all the outcomes are equally likely before you start, so perhaps with my my sort of system A and B being the same versus B being better, I might assume it's 50-50 on those. You get something that's very close to traditional statistics. It's not quite the same, but it's very, very close. And often that is what's done in a lot of Bayesian statistics. They assume a uniform prior where you can. Sometimes with unbounded ones, you have to put other distributions in. Now, looking at those two examples you had where we had the same data, the same evidence, we ran the study, we got the same thing, 4 users, preferred system B. On the prior where we thought, a very conservative one, things we probably haven't made any difference, you ended up with a non-overwhelming result, a 3-to-1 odds ratio. With the one where I assumed, I'm 80% sure my system is better, you end up with a 48-to-1 odds ratio and you think, wow, this is wonderful. That prior, the more belief you put in that of a particular outcome is going to happen, that then comes through into the posterior distribution. So there is a danger here of confirmation bias. Now, what you might do is deliberately be conservative, actually do the opposite, and perhaps demand overwhelming evidence, or you might, the more common thing is to take a uniform prior. But you do have to be careful. So sometimes there's good reasons. You have the data, you have the evidence for why your prior is not uniform, why you might think one thing is more likely than another. But as I said, you have to be incredibly careful not to let confirmation bias seek in. There are also issues with handling multiple evidence. So when you get, I said you got some evidence, but one nice thing you can do with Bayesian stats is you can take your posterior probability, which says, given the evidence to date, how likely do I think this is? You get some new evidence and you just slam it in and then you update and you hopefully build up perhaps your confidence that your new system is really better and eventually you release it. You do have to be a little careful to make sure, though, that the evidence you add is truly different evidence. To give you an idea of this, imagine you're sitting in an underground car park in a big building, and a car comes in, and you notice the front bonnet is wet. And you think, perhaps it's raining outside. But maybe it's just been to a car wash, or somebody with a bad cold sneezed over it, something. And it's damp for some other reason. Then you see another car, and you happen to notice, for some reason you don't notice the front bonnet because of where you're sitting, but you do notice the roof of the car is wet. And then another car comes in, and this time you miss the front bonnet and you miss the roof, but you do notice the top of the boot or the tailgate of the car at the back. You notice that's wet. And now you're starting to really think it must be pouring with rain out there. That's good, you're adding evidence in piece by piece. However, imagine that wasn't 3 cars. Imagine car comes in and you notice the front bonnet's wet, you notice the roof's wet, and you notice that the tailgate is wet. If you added those as 3 different bits of evidence, they're not, once one's wet, the others are likely to as well. They are not independent evidence. And you do have to be quite careful as you add evidence to not accidentally think you're adding different evidence, but it really is more of the same. So I said you have to be careful. I said you can do it, and in some ways it's really powerful, that ability to add evidence, and that's one of the reasons it's used in a lot of internal algorithms. But I said you also have to be a little bit careful of these interaction effects. I mean, it's one of the reasons why I spent quite a bit of time talking about independence and non-independence. It has various types of effect, and in Bayesian stats, perhaps even more than traditional stats, you have to be very careful of it. The other thing to note, and I am trying to be fair for this, but I have colours on my mass digest, but there is a little bit of internecine warfare in stats between the Bayesians and the traditional statisticians. It's been going on for, I think, 40 years probably, certainly longer than I've been involved in statistics, and I've been around for a fair old time. So I will try and be fair, take my words with a pinch of salt when I make comparisons, but also treat others with side. There's you know, it's not there's not a clear answer to what's the right thing to do, and we'll talk about that a little bit later. And I will nail some my colours to mass and make some suggestions about when's the appropriate time to use these. But as I said, it's a matter of debate and ongoing debate.